What if I told you everything we can see, the stars, the planets, even our own bodies, makes up less than 5% of the universe? The rest, a cosmic mystery so vast, so puzzling, that even the brightest minds on Earth are still scrambling to understand it. Welcome to the invisible frontier of dark matter and dark energy, the hidden forces shaping our universe in ways that defy everything we thought we knew. These aren't just scientific terms, they're the keys to unlocking the greatest secrets of existence itself. And today, we're diving deep into 25 mind-blowing facts that will leave you questioning reality as you know it. Picture this: galaxies spinning so fast they should tear themselves apart, yet something invisible holds them together. The universe expanding at an accelerating rate, pushed by a force we can't see or touch. These aren't plot twists from a sci-fi movie, they're real, observable phenomena, and they point to one astonishing truth: the cosmos is dominated by forces we've barely begun to comprehend. Dark matter, an elusive substance that doesn't interact with light, silently binds the universe together. Dark energy, an even more mysterious presence, is ripping space apart at the seams. Together, they make up 95% of everything that exists, and yet, we've never directly detected either of them. This isn't just a story about science, it's a detective tale on the grandest scale, one where every clue leads to more questions than answers. How can something so fundamental remain so hidden? What does it mean for the fate of the universe? And why, after decades of research, are we still grappling with these enigmas? Buckle up, because we're about to explore facts so strange, they'll warp your sense of reality. From ghostly particles that pass through you every second to the chilling possibility that our universe might one day vanish into nothingness, this journey will change how you see the cosmos forever. Ready to unravel the mysteries hiding in plain sight? Let's begin. Think about holding a snow globe. The tiny glittering flakes represent everything visible in our universe: stars, planets, gas, even us. Now imagine the entire globe filled with an invisible fluid outweighing the glitter 10 to 1. That's dark matter. It's everywhere, silently shaping the cosmos, yet it leaves no trace for our eyes or telescopes to catch. How do we know it's there? Because without it, galaxies would fly apart like spinning pizza dough flung into the air. Take the Bullet Cluster, one of the most striking pieces of evidence. When two galaxy clusters collided, their visible gas slammed together and slowed down, but something kept hurtling forward, bending the fabric of space behind it like a ghostly footprint. That something was dark matter, parting ways with the ordinary matter during the crash. It's as if you watched two crowds merge in a stadium, but their shadows kept walking straight through each other, unaffected. This cosmic shadow play proved dark matter isn't just a theory, it's a scaffold holding the universe together. And here's the wild part: for every ounce of visible matter, every star, every planet, every speck of cosmic dust, there's 5 times more dark matter tugging at it unseen. Picture a busy intersection where you only see the traffic lights but not the cars, yet somehow the lights keep stopping and going as if guided by invisible vehicles. That's the universe we live in, one where the rules we've always known barely scratch the surface. If dark matter is the universe's hidden scaffolding, dark energy is its ghostly engine, pushing space apart faster and faster in a cosmic acceleration that defies gravity itself. While dark matter keeps galaxies from flying apart, dark energy is doing the opposite, stretching the very fabric of reality. And here's the staggering part: it makes up 68% of everything in existence, dwarfing even dark matter in scale. This revelation came in 1998, when astronomers studying distant supernova made a spine-tingling discovery. These exploding stars, acting as cosmic mile markers, were fainter than expected, meaning space itself had stretched more than predicted during their light's journey to Earth. It was like tossing a ball in the air only to watch it shoot upward faster instead of falling back down. The universe wasn't just expanding, it was accelerating, propelled by some invisible pressure we now call dark energy. Picture blowing up a balloon with dots on its surface. Now imagine the balloon starts inflating faster on its own, the dots racing away from each other with no extra air being added. That's dark energy at work, an anti-gravity effect woven into space itself. Einstein actually predicted something similar with his cosmological constant, though he later dismissed it as his greatest blunder. Turns out he might have been right after all, just for reasons nobody could have guessed. What makes dark energy so baffling is how little we understand its nature. It could be a property of empty space gaining strength as the universe grows, or an entirely new force field still hidden from our equations. Some theories even suggest it might fluctuate over time, potentially one day tearing atoms apart in a catastrophic Big Rip. What we do know is this: dark energy's grip is tightening, and its ultimate fate could rewrite the destiny of everything that exists. Here's the cosmic irony: dark matter could be flowing through you right now, and you'd never know it. Unlike ordinary matter, which dances with light, dark matter doesn't emit it, absorb it, or even reflect it. It's the universe's ultimate phantom, invisible to every telescope ever built. So how do we know it's there? Because it bends reality itself. Take gravitational lensing, nature's magnifying glass. When light from distant galaxies passes through a cluster of dark matter, the unseen mass warps space-time, distorting the light like a funhouse mirror. Astronomers see stretched or duplicated images of galaxies where none should exist, an eerie signature of something massive but invisible bending the light's path. It's like watching ripples in a pond and realizing something beneath the surface is disturbing the water, even though you can't see the object itself. Then there's the way galaxies spin. Stars on the outer edges of spiral galaxies move far faster than they should, as if gripped by an unseen hand. Without dark matter's gravitational pull, these stars would fling into the void, yet they cling to their orbits like marbles glued to a spinning plate. For decades, scientists have tried to explain this with tweaks to gravity laws, but the math never adds up unless something invisible is holding the universe together. And here's the kicker: despite countless experiments, dark matter has never been caught in the act. Underground labs hunt for hypothetical particles like WIMP, weakly interacting massive particles, shielded from cosmic noise by miles of rock. Particle colliders smash atoms together, hoping to create dark matter in miniature explosions. So far, silence. It's like hearing footsteps in an empty house, finding every door locked, and realizing you're not just missing a key, you might not even know what the lock looks like. This isn't just a technical hurdle, it's a fundamental gap in our understanding of reality. Dark matter's elusiveness forces us to question whether we're searching for a particle, or something stranger, like an undiscovered dimension or a flaw in Einstein's relativity. Every null result isn't a dead end, it's a signpost pointing toward a deeper mystery, one that might rewrite the rules of physics as we know them. The Milky Way should be tearing itself to shreds right now. At the speed our galaxy spins, over 200 kilometers per second at the outer edges, Newton's laws say all those stars should go flying into the void like sparks from a grinding wheel. Yet they don't. Instead, they cling to their orbits with eerie stability, as if tethered by invisible ropes. The reason? A vast, unseen halo of dark matter, 10 times more massive than all the stars and gas combined, wrapping around our galaxy like an immense gravitational net. Here's the math that left astronomers stunned. Based on visible matter alone, stars farther from the galactic center should move slower, just like planets in our solar system. Mercury zips around the sun faster than Neptune. But when scientists measured the Milky Way's rotation curve, they found something bizarre. Stars at the edge were moving just as fast as those near the middle. It's as if a playground merry-go-round kept spinning at the same speed whether you stood at the center or clung to the outer edge. This wasn't just a quirk, it was a screaming anomaly that shattered classical physics. The only way to explain it, an enormous amount of unseen mass, its gravity reaching far beyond the galaxy's visible disk. Picture a city where streetlights mark the edges of town, but traffic cameras keep catching cars racing past them at full speed, as if the real city extended miles into the darkness. That's the Milky Way. What we see is just the illuminated tip of a shadowy iceberg. Without dark matter's pull, our galaxy, and every other spiral galaxy in the universe, would have flung itself apart billions of years ago. Even more mind-bending, dark matter doesn't just hug galaxies, it connects them. Vast filaments of this mysterious substance form a cosmic web, with galaxies clustered like dewdrops on a spider's silk. These threads stretch across unfathomable distances, guiding the universe's large-scale structure. When astronomers map the distribution of galaxies, they're essentially tracing the fingerprints of something far greater, an unseen architecture written in gravity itself. Yet for all its influence, dark matter remains maddeningly aloof. It doesn't clump like ordinary matter. It can't form dense objects like planets or black holes. Instead, it drifts through space in diffuse clouds, refusing to interact except through gravity. This is why some scientists compare it to a cosmic ghost, ubiquitous, powerful, but forever slipping through our fingers. The more we learn, the clearer it becomes. Dark matter isn't just holding galaxies together. It's the silent architect of everything we see, a shadowy puppet master we've only just begun to notice. Imagine the universe as a loaf of raisin bread baking in an oven, except the dough keeps stretching faster and faster, pushing every raisin away from the others at an ever-increasing speed. That's dark energy's handiwork, an invisible force not just expanding space, but accelerating that expansion with each passing moment. At first glance, this might sound like a gentle cosmic process, but its long-term consequences are anything but peaceful. If dark energy continues unchecked, it could one day stretch the fabric of reality so violently that galaxies, stars, and even atoms themselves are torn apart in a catastrophic event cosmologists call the Big Rip. Here's how the clock ticks toward cosmic destruction. Right now, dark energy's push is subtle. The space between galaxies grows, but gravity still holds galaxies and galaxy clusters together. But over billions of years, as dark energy's influence grows stronger, those bonds will start to falter. First, galaxy clusters would be ripped apart, sending galaxies adrift like boats cut from their moorings. Next, individual galaxies would unravel, their stars flung into the void. In the final moments, even the stars themselves would disintegrate as the force between atoms is overcome. It's as if the universe itself decided to hit the fast-forward button on its own dissolution. The balloon analogy helps visualize this. Blow up a balloon slightly, and the dots on its surface move apart slowly. Now imagine the balloon starts inflating on its own, faster and faster. Soon, the dots are racing away so quickly that the rubber between them stretches to the breaking point. That's the Big Rip in action. Unlike the Big Crunch where gravity pulls everything back together, or the heat death where the universe expands into cold silence, the Big Rip is a violent, dramatic end, one where dark energy doesn't just empty the cosmos but actively shreds it. What makes this scenario so unsettling is its inevitability if dark energy behaves as some models predict. Unlike other cosmic doomsdays, there's no maybe in the equations, just a countdown. Current estimates suggest this could happen in about 22 billion years, though the uncertainty is vast. Some theories even propose dark energy might fluctuate, its strength waxing and waning like a tide. But if it continues gaining strength, no force in the universe, not gravity, not nuclear bonds, will be able to resist it. Yet here's the twist: dark energy's expansion might also be the reason we're alone in the universe. As space stretches, distant galaxies will eventually move away faster than light can bridge the gap, vanishing from our view forever. Civilizations born too late in cosmic history will see only an empty void outside their local galaxy cluster, with no evidence that a vast universe ever existed. It's a haunting thought. The very force that keeps the universe alive today might one day erase all traces of its existence, leaving future astronomers with a sky full of unanswered questions. If dark matter were a criminal, WIMP and axions would be the prime suspects, hypothetical particles so elusive they make ghosts look obvious. Scientists have spent decades chasing these phantom-like entities, and while neither has been caught red-handed yet, the hunt has transformed underground labs into cosmic detective agencies. Weakly interacting massive particles, or WIMP, are the James Bonds of the particle world, stealthy, heavy, and interacting only through gravity and the weak nuclear force. Picture trying to catch a bulletproof spy who only leaves fingerprints in invisible ink. That's the challenge facing experiments like the LUX Zeppelin detector, buried a mile underground in a former South Dakota gold mine. Shielded from cosmic rays by a fortress of rock and water, it waits for the faintest flicker of light or heat, a sign that a WIMP has finally bumped into an atom of liquid xenon. The setup is so sensitive it could detect a single snowflake landing on a roof. Yet after years of operation, the silence is deafening. Then there are axions the quantum will owe the WISPs. Unlike WIMP, these particles are feather-light, possibly 1 billion times less massive than an electron. Theory suggests they were born in the chaos of the early universe, flickering into existence like cosmic static. To catch them, scientists built devices like the axion dark matter experiment, which uses powerful magnets to convert axions into microwaves akin to tuning a radio to a station that might not even exist. It's a gamble, but one worth taking. If axions are real, they could solve two mysteries at once, explaining dark matter and fixing a nagging inconsistency in particle physics called the strong CP problem. The stakes couldn't be higher. Discovering WIMP would validate decades of theory rooted in supersymmetry, a framework that elegantly extends the standard model of physics. Axions, on the other hand, emerge from quantum field theory's stranger corners, offering a minimalist solution that avoids new, unseen forces. Both candidates have armies of physicists betting on them, and both could rewrite our understanding of reality. Yet the longer the search drags on, the more scientists wonder, what if dark matter isn't a particle at all? Could it be primordial black holes forged in the universe's first second? Or something even wilder, like particles from a hidden dimension? The lack of definitive proof isn't a failure, it's a reminder that the universe guards its secrets fiercely. Every null result narrows the search, forcing us to question assumptions and dig deeper into the unknown. Meanwhile, newer experiments are pushing boundaries. The upcoming super cryogenic dark matter search will chill its detectors to near absolute zero, hunting for axions with precision never before achieved. And at CERN, physicists are colliding protons at unprecedented energies, hoping to create dark matter in miniature supernova. Each effort is a high-stakes roll of the dice, with the potential to crack open the cosmos's biggest mystery, or send us back to the drawing board once again. Here's the irony: dark matter could be raining down on us right now, passing through our bodies by the billions every second. Yet without a whisper of interaction, it remains as intangible as a rumor. The quest to pin it down isn't just about filling a gap in our equations. It's about proving we have what it takes to see the unseen. Whether WIMP, axions, or something beyond our current imagination, the answer is out there, lurking in the shadows, waiting for its moment to step into the light. Einstein once scribbled a number in the margins of his equations, a tiny mathematical fudge factor he called the cosmological constant. It was 1917, and the prevailing belief was that the universe stood still, neither expanding nor contracting. But Einstein's own general theory of relativity suggested otherwise. The cosmos should either collapse under gravity or stretch apart. Uncomfortable with that idea, he inserted this constant as a cosmic brake, a repulsive force to balance gravity and keep the universe static. It was elegant, simple, and, as he later admitted, perhaps the greatest mistake of his career. The irony, he was right for all the wrong reasons. When Edwin Hubble discovered in 1929 that galaxies were racing away from each other, proving the universe was expanding, Einstein dismissed his own constant as unnecessary. He called it superfluous and theoretically unsatisfactory, stripping it from his equations like a builder removing scaffolding after finishing a house. For decades, the cosmological constant became a footnote, a cautionary tale about overcomplicating physics. Then came the bombshell of 1998. Astronomers measuring distant supernova found the universe wasn't just expanding, it was accelerating, as if some invisible pedal was pressed to the cosmic floor. The only explanation, a repulsive force eerily similar to Einstein's discarded constant. Suddenly, his blunder wasn't a mistake, it was a prophecy. The cosmological constant had morphed into dark energy, the very thing driving the universe apart at breakneck speed. What's fascinating isn't just that Einstein stumbled upon the answer decades early, it's why he rejected it. His instincts were rooted in the science of his time. A static universe seemed obvious, the idea of space itself stretching was outrageous. Even when mathematician Alexander Friedmann showed Einstein's equations allowed for expansion, Einstein reportedly replied, "Your calculations are correct, but your physics is abominable." It wasn't until Hubble handed him observational proof that he relented, calling his resistance the biggest blunder of my life. Yet today, the joke's on us. Dark energy remains as baffling as ever. Is it truly a constant as Einstein imagined, or something dynamic, changing over time? Could it eventually vanish, or worse, grow strong enough to tear atoms apart? The cosmological constant's resurrection proves even geniuses can't predict which ideas will rise from the grave. Einstein spent years running from his own insight, only for the universe to shout it back at us a century later. Here's the kicker: had Einstein trusted his original equations, he might have predicted cosmic acceleration before Hubble found expansion. Instead, his quest for a tidy, static universe blinded him to the chaos lurking in the math. It's a lesson that still haunts physicists. Sometimes the truth hides in the very ideas we're too quick to throw away. Now, every time astronomers measure dark energy's grip on the cosmos, they're unknowingly testing a number Einstein once scribbled down then crossed out. The universe, it seems, has a way of circling back to the answers we least expect. What if dark matter isn't made of exotic particles at all, but something far stranger: black holes born in the universe's first chaotic moments? This audacious idea, once relegated to the fringes of cosmology, has gained startling traction in recent years thanks to a series of gravitational wave detections that left scientists questioning everything they thought they knew. Picture the infant universe, less than a second old, a seething cauldron of energy where space itself bubbled like boiling water. In these extreme conditions, theorists suggest pockets of matter may have collapsed directly into black holes, not the kind formed by dying stars, but primordial ones forged in the furnace of the Big Bang. These ancient relics, some as light as an asteroid or as heavy as 1,000 suns, could be lurking everywhere, invisible yet omnipresent. If they exist, they'd explain dark matter's gravitational grip without requiring undiscovered particles. The game changer came in 2015 when LIGO, the Laser Interferometer Gravitational Wave Observatory, detected ripples in space-time from colliding black holes 30 times the sun's mass, far heavier than expected. Conventional astrophysics couldn't easily explain their origin, but primordial black holes, they fit the bill perfectly. Later observations only deepened the mystery. Some black hole mergers involved objects in the so-called mass gap, a range theory says shouldn't exist for stellar-born black holes. It's like finding footprints in a forest where no animal should have left them. Here's where it gets wild. If primordial black holes make up even a fraction of dark matter, they'd be everywhere, floating between stars, drifting through galaxies, maybe even orbiting our solar system. Unlike WIMP or axions, they wouldn't need new physics to exist. They're just black holes that skip the usual stellar life cycle, but proving it, that's the catch. These ancient holes would be pitch black, emitting no light, and smaller ones could have evaporated by now due to Hawking radiation. Spotting them would require ingenious tricks, like watching for the brief flicker when one passes in front of a star, bending its light like a cosmic magnifying glass. Skeptics point out major hurdles. Too many primordial black holes would have altered the cosmic microwave background, the afterglow of the Big Bang, in ways we don't see. They also should have gobbled up neutron stars, leaving voids in galaxies where these dense stars are mysteriously absent. Yet alternative models suggest a Goldilocks range, black holes between 10 and 1,000 solar masses, that could evade these constraints while still accounting for dark matter's pull. The debate rages on, but one thing's certain: if primordial black holes are real, they'd rewrite cosmic history. They might have seeded the first galaxies, provided the scaffolding for stars to form, or even birthed supermassive black holes lurking at galactic centers. Some theorists even speculate they could be portals to other universes or relics of a previous cosmic cycle. Every gravitational wave detection now carries a tantalizing question. Are we hearing echoes of the universe's birth, the whispers of its hidden architecture? Until we know for sure, these ancient shadows remain both a compelling solution and a profound mystery, one that challenges us to rethink the very fabric of reality. Here's something that defies common sense. Imagine pouring a cup of water into an expanding pool, but no matter how much the pool grows, the water never thins out. That's dark energy in a nutshell. Unlike matter, which dilutes as the universe stretches, its particles spreading farther apart, dark energy's density remains stubbornly constant. Every new cubic meter of space that forms comes with its own built-in dose of this repulsive force, as if the cosmos is printing dark energy on demand. This bizarre property flips our intuition upside down. Think of matter like ink dropped into water. As the volume increases, the color fades. But dark energy behaves like an infinite ink supply, maintaining its intensity no matter how vast the cosmic ocean becomes. The implications are staggering. Billions of years ago, matter ruled the universe, its gravity pulling galaxies together. But as space expanded, matter's influence weakened while dark energy's grip held firm. Around 5 billion years ago, the tide turned. Dark energy became dominant, and the universe shifted from slowing its expansion to accelerating. Now here's where it gets eerie. If dark energy's density truly never changes what physicists call the cosmological constant scenario, its dominance will only grow. Over trillions of years, galaxies beyond our local group will vanish over the cosmic horizon, their light stretched beyond detectability. The universe will become a vast, empty desert with isolated island galaxies drifting endlessly apart. But if dark energy's strength increases over time, a nightmare scenario called phantom energy, the acceleration could spiral out of control. Space itself might rip apart galaxy clusters, then stars, then planets, and finally atomic bonds in a catastrophic Big Rip. The key to this puzzle lies in dark energy's nature. If it's truly baked into the fabric of space, a property of the vacuum itself, then its constancy makes sense. But if it's a dynamic field, like an invisible fluid with changing pressure, all bets are off. Some theories suggest it could decay, reversing acceleration one day. Others warn it might grow stronger, turning the universe into a runaway expansion engine. What's certain is this: dark energy's unchanging density isn't just a quirky detail, it's the reason our universe's fate hangs in the balance. While matter's influence fades like an echo, dark energy's whisper grows louder with every new inch of space it creates. The cosmos isn't just expanding, it's being rewritten by a force that never tires, never weakens, and refuses to play by the rules we know. Gravity is the universe's ultimate architect, and dark matter is its blueprint. While galaxies glitter like cities at night, they're not scattered randomly. They're strung along vast, invisible highways of dark matter, forming a cosmic web that stretches across the observable universe. This isn't poetic exaggeration. It's the backbone of reality, a scaffold so immense that if you could see it, the entire structure would resemble a neural network lighting up the cosmos. Computer simulations reveal the web's spine-tingling scale. Start with the early universe, a nearly smooth soup of matter and dark matter. As gravity works its magic over billions of years, dark matter clumps first, pooling in dense regions like dew gathering on a spider's silk. Ordinary matter, the gas and dust that make stars and planets, follows these gravitational wells, flowing along dark matter's hidden contours. The result: filaments of galaxies millions of light-years long, intersecting at colossal knots where galaxy clusters collide, all threaded together by dark matter's unseen hand. One of the most striking examples is the Sloan Great Wall, a filament of superclusters stretching over 1.4 billion light-years, a structure so vast it challenges our understanding of cosmic limits. Then there's the Pisces-Cetus supercluster complex, a web of galaxies so extensive it makes our local group feel like a speck of dust in a cathedral. These aren't random accidents, they're the fingerprints of dark matter's gravitational influence, a pattern repeated across the universe like a fractal. Here's the twist: without dark matter, this web wouldn't exist. Ordinary matter alone couldn't clump fast enough after the Big Bang to form such intricate structures. Radiation pressure would have blown gas apart before galaxies could take shape. Dark matter, indifferent to light's push and pull, provided the gravitational anchor that let the universe build itself. It's like trying to construct a skyscraper in a hurricane. Only with an invisible framework holding everything in place could the visible materials assemble against the chaos. Yet the web isn't static. It breathes and evolves, with dark matter filaments funneling galaxies toward clusters in slow-motion collisions that last eons. Hubble's deep field images catch glimpses of this dance: galaxies aligned like pearls on a string, their positions betraying the unseen threads between them. Even our Milky Way is part of this grand design, being pulled toward the Great Attractor, a mysterious gravitational anomaly hidden behind the dust of our own galaxy. The cosmic web is more than just structure. It's a living map of the universe's history and destiny. By tracing its filaments, astronomers can reconstruct how dark matter shaped the cosmos from infancy to today. And somewhere in those tangled threads lies the answer to why the universe looks the way it does, not as scattered islands, but as an interconnected masterpiece woven together by the darkest, most elusive substance in existence. The emptier space gets, the more energy it seems to hold, a paradox that lies at the heart of one of physics' greatest puzzles. Quantum mechanics tells us that a true vacuum isn't empty at all. Instead, it's a seething quantum foam where particles and antiparticles flicker in and out of existence faster than the blink of an eye. These fleeting fluctuations generate zero-point energy, a background hum of the universe that never quiets down. And here's the shocker: when physicists calculate how much energy this quantum buzz should contribute to space, the numbers are catastrophically wrong, off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, a discrepancy so vast it's been called the worst theoretical prediction in the history of science. This is the cosmological constant problem in all its glaring absurdity. If empty space really contains this much intrinsic energy, dark energy's effect should be a trillion times stronger than what we observe. The universe would have torn itself apart before atoms could even form. Yet when astronomers measure dark energy's actual strength, it's whisper weak, just enough to nudge galaxies apart at an accelerating rate. It's as if you expected a hurricane and got a breeze strong enough to sway a dandelion. So where's the disconnect? One possibility is that opposing effects cancel out almost perfectly, leaving behind only a faint residue we call dark energy. Imagine pouring a cup of boiling water into the ocean. The immense volume neutralizes the heat until it's undetectable. Similarly, some theorists suggest unknown symmetries or mechanisms in quantum fields might balance the vacuum's raging energy, with dark energy being the tiny imbalance left over. Others propose space has a sort of memory limit. It can only hold so much zero-point energy before hitting a cosmic saturation point, like a sponge that stops absorbing water. Then there's the radical idea that dark energy isn't vacuum energy at all, but something entirely different, a new field or a side effect of extra dimensions. String theory, for instance, predicts a landscape of possible universes, each with its own vacuum energy. In this scenario, we just happen to live in one where the value is oddly small, like winning a lottery where the prize is almost nothing. It's unsatisfying, but it highlights how desperate physicists are to solve this enigma. What makes this problem so maddening is that it pits quantum mechanics against cosmology, two of our most successful theories, yet they clash spectacularly here. Quantum calculations say space should burst with energy. Observations say it barely registers. Bridging this gap may require rewriting our understanding of gravity, quantum fields, or the very nature of space itself. Until then, dark energy remains a riddle wrapped in the vacuum of space, an invisible force we can measure but still can't explain. Here's the cosmic twist that makes dark matter even stranger. When two galaxy clusters collide in a spectacular cosmic wreck, their dark matter seems to ghost right through itself like two crowds of phantoms merging without a single handshake. This bizarre behavior was caught in action with El Gordo, a colossal cluster collision 7 billion light-years away, where telescopes observed something that defies everything normal matter does. Visible matter, the gas and stars within these clusters, slammed together violently, heating up and glowing in X-rays like metal forged in a furnace. But the dark matter, mapped through gravitational lensing, didn't slow down or scatter. Instead, it sailed right past its own kind, undisturbed. It's as if you threw two handfuls of sand into the wind and watched the grains pass through each other like holograms, never actually touching. This ghostly pass-through effect suggests dark matter particles might lack something fundamental, interactions beyond gravity. Normal matter crashes, clumps, and creates friction because of electromagnetic forces. Protons repel protons, electrons bond with nuclei, and gas particles collide, radiating heat. But dark matter, it could be utterly antisocial, ignoring everything except gravity's pull. Simulations support this. If dark matter particles did collide, even rarely, they'd lag behind during mergers, leaving visible traces in lensing patterns. Yet El Gordo and others like the Bullet cluster show no such hesitation. The implications rattle our understanding of particle physics. If dark matter truly doesn't interact with itself, it can't be made of particles like protons or electrons, which are chatty by nature. Instead, it might belong to a shadowy class of particles that barely acknowledge the universe's social rules. No electromagnetic handshakes, no strong force high fives, just gravity's silent nod. Some theories propose sterile neutrinos, hypothetical particles even more aloof than regular neutrinos, which already pass through planets like they're not there. Others suggest entirely new forces operating only in the dark sector. Yet mysteries linger. A few observations, like the oddly dense core of certain dwarf galaxies, hint that dark matter might occasionally interact just enough to smooth out clumps without full collisions. It's like finding a single fingerprint at a crime scene where the suspect was supposed to leave no trace. Could dark matter have subtle interactions we've yet to detect, or are these cosmic outliers red herrings? The answer could rewrite particle physics. If dark matter truly ignores itself, our universe is filled with a substance fundamentally alien to everything we know, a cosmic spectator that builds galaxies without ever touching its own kind. Every collision we observe is another clue in this interstellar detective story, where the culprit leaves no fingerprints, only gravity's shadow. In 1998, astronomers made a discovery so shocking it upended cosmology's foundational assumptions and earned them a Nobel Prize. The universe wasn't just expanding, it was accelerating, as if some unseen force had pressed the cosmic gas pedal. The key to this revelation, Type Ia supernova, the universe's most reliable light bulb. These dying stars explode with such consistent brilliance that astronomers use them as standard candles, cosmic mile markers to measure vast distances. When two separate teams studied these supernovae across billions of light years, they expected to confirm the long-held belief that gravity was gradually slowing the expansion. Instead, they found the opposite. The most distant supernovae were dimmer than predicted, meaning space had stretched more during their light's journey, proof the expansion was speeding up. The implications were staggering. Imagine tossing a ball into the air, expecting it to slow and fall back, only to watch it shoot skyward faster and faster. That's what the data showed. Gravity, the force that sculpts galaxies and bends light, was losing a tug of war against something far more powerful. Theorists scrambled for explanations, but only one fit: dark energy, a repulsive force embedded in space itself, pushing galaxies apart with increasing vigor. What makes Type Ia supernova so crucial is their uniformity. Whether they occur in a young galaxy or an old one, these explosions reach nearly identical peak brightnesses because they're triggered when white dwarf stars reach a specific critical mass. This consistency lets astronomers calculate their true distance versus their apparent brightness, and thus, how much the universe has stretched since their light began traveling. The teams, led by Saul Perlmutter and Brian Schmidt with Adam Rees, measured dozens of these supernovae, cross-checking their results like detectives verifying alibis. The conclusion was inescapable. The universe's expansion wasn't coasting. It was accelerating, driven by a mysterious energy that made up 2/3 of everything. This discovery didn't just add a new chapter to cosmology, it tore up the old playbook. For decades, scientists had assumed the universe's fate would hinge on a simple question: was there enough matter to eventually halt and reverse the Big Bang's outward rush? Now they faced a baffling third option: an expansion that would continue indefinitely, growing faster until galaxies beyond our local group vanished over the cosmic horizon. Even Einstein's once discarded cosmological constant, a mathematical fudge factor he'd called his greatest blunder, was resurrected as a potential explanation. The acceleration's breakneck pace raises chilling questions. If dark energy's push grows stronger over time, it could one day overcome gravity's grip on galaxies, then stars, then atoms, a theoretical doomsday called the Big Rip. But for now, those distant supernovae serve as both mileposts and warnings, reminding us that the universe's greatest forces are still hiding in plain sight. Every time astronomers measure one of these cosmic explosions, they're not just charting distances, they're tracing the fingerprints of a mystery we're only beginning to grasp. Long before the first stars flickered to life, dark matter was already shaping the cosmos in profound ways we're only beginning to understand. Picture the universe just 400,000 years after the Big Bang, a hot, dense fog of plasma where light and matter were locked in a chaotic dance. Ordinary matter, burdened by the constant push and pull of radiation, couldn't clump together. Every time atoms tried to form, photons would slam into them like a cosmic game of pinball, scattering particles apart. But dark matter, indifferent to light's bullying, was already gathering in silent, invisible pools under its own gravity. These dark matter halos became the universe's first skeletons, gravitational anchors that gave ordinary matter something to cling to. Without them, the gas that would eventually form stars and galaxies would have been blown across the cosmos like dust in a hurricane. Think of it like trying to build sandcastles on a windy beach. Without a barrier to block the gusts, your structure collapses. Dark matter provided that shelter, creating deep wells of gravity where hydrogen and helium could finally settle, cool, and ignite the first stars. The evidence for this lies in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal where dark matter had already begun clustering, creating gravitational blueprints for future galaxies. These patterns show that dark matter's structure formation was well underway while ordinary matter was still trapped in a glowing, opaque soup. It's as if the universe had two construction crews, one working in the dark, laying foundations at lightning speed, while the other waited for the storm to pass before they could start building. Here's the kicker: without dark matter's head start, galaxies like ours might never have formed in time. The first stars, known as population 3 stars, blazed to life hundreds of millions of years earlier than they could have without dark matter's gravitational assist. These stellar pioneers were massive and short-lived, seeding the cosmos with heavier elements that would later form planets and life. Every atom in your body owes its existence to those early stars and, by extension, to dark matter's unseen scaffolding. Yet this raises a haunting question. If dark matter hadn't existed or behaved differently, would the universe be a vast, empty void? The answer lies in simulations where physicists remove dark matter from cosmic equations. The result is a desolate expanse where galaxies either form too late or not at all. Dark matter wasn't just present first, it was the universe's ultimate enabler, turning a formless sea of particles into the glittering web of galaxies we see today. Its gravitational whisper didn't just shape space, it made the very possibility of stars, planets, and us inevitable. What if dark energy isn't a constant force, but something far more dynamic, a cosmic chameleon shifting its strength over time? This idea, known as quintessence, upends everything we thought we knew about the universe's fate. Unlike the static cosmological constant, Einstein's once discarded concept revived to explain dark energy, quintessence suggests the repulsive force accelerating the cosmos could be weakening, strengthening, or even flipping its effects entirely. Picture a car's cruise control suddenly turning into a temperamental gas pedal, sometimes surging forward, other times easing off. That's the unpredictable future quintessence paints for our universe. The cosmological constant model is simple. Dark energy's density stays uniform, woven into space itself like an immutable law of physics. But quintessence proposes something wilder, a field or fluid permeating space, its pressure fluctuating as the universe evolves. Some versions suggest dark energy was stronger in the past, explaining why the universe's expansion took 5 billion years to shift from deceleration to acceleration. Others hint it might fade away entirely, allowing gravity to regain control and potentially collapse the cosmos in a big crunch, the most unsettling possibility. Phantom energy, a form of quintessence that grows endlessly stronger, destined to tear apart galaxies, stars, and even atoms in that catastrophic Big Rip scenario. Evidence for these theories hides in the subtle dance of supernova and galaxy clusters. By measuring how expansion rates changed across cosmic time, astronomers hunt for wiggles in the day to tiny deviations from the cosmological constant's predictions. It's like tracking a suspect's footsteps. If dark energy were truly constant, the footprints would deepen uniformly. But if they vary, sometimes light, sometimes heavy, it points to something more fluid, more alive. The Dark Energy Survey and upcoming missions like Euclid are scouring the skies for these clues, comparing ancient supernova, galaxy distributions, and even the bending of light to test quintessence's fingerprints. Here's where it gets even stranger. Some quintessence models allow dark energy to interact with dark matter, exchanging energy in ways that could reshape the cosmic web. Others propose it triggered the universe's initial inflation epoch before lying dormant for billions of years, like a hibernating dragon stirring awake. The most radical versions suggest dark energy might not be a single phenomenon at all, but the cumulative effect of undiscovered dimensions or quantum gravity's quirks. Yet for all its intrigue, quintessence remains a gamble. The cosmological constant, despite its unanswered questions, matches observations with eerie precision. Changing dark energy would leave observable scars on the cosmic microwave background, or the large-scale structure of galaxies, scars we haven't convincingly found. But the hunt continues because the stakes couldn't be higher. If dark energy shifts even slightly over time, it doesn't just alter the universe's fate, it rewrites the rules of physics itself. Every measurement, every distant supernova brings us closer to answering one haunting question. Are we living in a universe governed by static simplicity, or one where the very fabric of reality is still evolving beneath our feet? What if dark matter isn't just a lone actor in the cosmic play, but part of an entire invisible universe complete with its own particles, forces, and maybe even dark stars? This wild idea, known as the dark sector, suggests dark matter isn't merely passive scaffolding, but a bustling hidden realm governed by rules we've yet to discover. Think of it like an iceberg. What we see in galaxies and clusters might just be the tip, with a whole shadowy world lurking beneath the surface. The dark sector hypothesis hinges on one simple question: why should all the complexity be reserved for visible matter? Our universe teems with particles, quarks, electrons, neutrinos, each interacting through forces like electromagnetism and the strong nuclear force. If dark matter outweighs normal matter 5 to 1, wouldn't it make sense for it to have its own rich structure? Theorists speculate about dark photons, hypothetical particles acting as messengers for a dark version of electromagnetism, or even dark atoms clumping into dark planets and dark galaxies. It's not science fiction, it's a legitimate attempt to explain why dark matter behaves so differently from everything else we know. Hints of this hidden complexity come from odd cosmic observations. Some dwarf galaxies, for instance, show dark matter distributions that are smoother than simulations, predict as if something were preventing it from clumping too densely. If dark matter particles interacted through their own force, even weakly, those collisions could spread them out like marbles scattering on a floor. Similarly, certain gravitational lensing patterns hint at subtle interactions beyond gravity's pull. It's like watching tree branches sway and realizing there's not just wind at work. Maybe an unseen creature is moving among them. To hunt for these phantom forces, scientists have turned to underground labs and particle colliders. Experiments like the Large Hadron Collider aren't just smashing protons to find dark matter, they're searching for evidence of dark photons, which could occasionally leak into our visible universe. Imagine two parallel worlds separated by a thin curtain. Sometimes a breeze might rustle the fabric between them. If dark photons exist, they could momentarily bridge that gap, leaving faint signatures in detector data. Other projects, like the proposed beam dump experiment, bombard materials with electrons, hoping to spark dark particles into revealing themselves. The implications are staggering. A confirmed dark force would mean our universe is just one layer of a far richer reality, like discovering your house has secret rooms behind every wall. It could explain why dark matter resists detection, not because it's simple, but because it's part of a vast, invisible ecosystem obeying its own rules. Some theories even suggest dark matter might undergo phases like freezing or evaporating under the influence of these hidden forces, yet skeptics warn against overcomplicating the mystery. Dark matter's ghostly pass-through behavior in galaxy collisions suggests any dark sector interactions must be incredibly rare, and without direct evidence, the dark sector remains a tantalizing what-if. But that's the thrill of science at the edge of discovery. Sometimes the boldest ideas are the ones worth chasing, even if they lead us deeper into the unknown. After all, history shows the universe rarely settles for simplicity when complexity is an option. Stars on the outer edges of spiral galaxies are cosmic speed demons. They whip around galactic centers so fast that by all known physics, they should have been flung into the void eons ago. Picture a carnival ride spinning so violently that everyone clinging to the edges goes flying, except nobody does. That's the galaxy rotation problem in a nutshell, a puzzle so baffling it forced astronomers to rewrite the rules of the cosmos. The breakthrough came thanks to Vera Rubin, a tenacious astronomer who refused to let skepticism stand in her way. In the 1970s, while studying the Andromeda Galaxy, she meticulously tracked the orbital speeds of stars at different distances from the center. Newton's laws dictated that stars farther out should move slower, just as Pluto crawls compared to Mercury. But Rubin's data revealed something astonishing. Stars at the galaxy's edge raced just as fast as those near the core, as if some unseen hand kept them glued in place. The math was clear. Andromeda's visible mass couldn't account for this velocity without tearing itself apart. Gravity alone insisted there had to be 5 times more matter than anyone could see. Rubin's findings echoed earlier work by Fritz Zwicky, who in the 1930s noticed galaxies in clusters moved too quickly for their visible mass. But where Zwicky's observations were dismissed as fringe, Rubin's precise measurements shattered doubt. She didn't just spot an anomaly, she exposed a universal truth. Every spiral galaxy she studied, dozens in total, displayed the same impossible rotation. The implications were unavoidable. Galaxies are cocooned in vast halos of invisible matter, its gravitational grip the only thing preventing them from disintegrating. Here's why this flips intuition on its head. Imagine swinging a yo-yo in a circle. The faster you spin it, the harder you must tug the string to keep it from flying away. Now replace your hand with a weak magnet and the yo-yo with a steel ball. If the magnet's pull isn't strong enough, the ball escapes. Yet galaxies spin with the equivalent of that weak magnet's pull, their outer stars orbiting at speeds that should require 10 times the visible gravity. The only explanation: dark matter's invisible tether wrapping around galaxies like a gravitational safety net. Modern simulations drive the point home. Plug in only visible matter and virtual galaxies spin apart within rotations. Add dark matter and they stabilize into the majestic spirals we observe. It's not just about speed, it's about structure. Without dark matter's scaffolding, galaxies as we know them wouldn't exist. Rubin's work didn't just uncover a mystery, it revealed the silent architect behind every swirling disk of stars in the night sky. Yet resistance lingered for years. Some theorists scrambled to tweak gravity itself, proposing modified Newtonian dynamics, MUND, as an alternative. But MUND struggles to explain cosmic web formations or galaxy cluster collisions where dark matter's presence is etched in gravitational lensing. Rubin's verdict stands: the universe is saturated with something we can't see, and its fingerprints are written in the star's relentless, impossible speed. Every time you gaze at a spiral galaxy, remember, you're not just seeing stars, you're witnessing the shadow of a deeper reality, one where the visible universe is just the tip of an invisible iceberg, and the rules of the cosmos are still being rewritten. What if dark energy isn't real, just a cosmic mirage created by our misunderstanding of gravity itself? This radical idea suggests we've been chasing a phantom, and the universe's accelerating expansion might stem not from some mysterious energy, but from gravity behaving differently on colossal scales than Einstein predicted. Enter modified Newtonian dynamics, a theory that dares to rewrite the rules of gravity to explain galactic motions without invoking invisible dark matter or energy. MUND's premise is simple yet revolutionary. Instead of adding dark matter to explain why stars orbit galaxies too fast, maybe Newton's and Einstein's laws break down when gravity becomes incredibly weak, like at the fringes of galaxies. Imagine a car that mysteriously speeds up when you ease off the gas. Instead of inventing an invisible engine pushing it, MUND suggests the accelerator pedal itself works differently at low pressure. The math fits surprisingly well for individual galaxies. neatly matching rotation curves without requiring halos of dark matter. But here's the catch. WIMPs struggles to explain the bullet clusters and cosmic web structures where dark matter's gravitational fingerprints are undeniable. Then there's the dark energy challenge. Even if man could tweak gravity to replace dark matter, cosmic acceleration demands an additional fix. Some theorists propose relativistic extensions of WIMPs, like TVS tensor vector scalar gravity, which add extra fields to mimic dark energy's repulsive push. Yet these models often feel like Rube Goldberg machines' overly complicated patches that lack the elegance of Einstein's original equations. Worse, they fail to predict the observed patterns in the cosmic microwave background or the large-scale distribution of galaxies as precisely as the standard dark energy model. So why does dark energy remain the leading explanation? Because it's the simplest framework that fits all the data, from supernova to galaxy clustering to the afterglow of the Big Bang. Scientists love Occam's razor. When multiple lines of evidence point to one conclusion, the least convoluted solution is usually correct. Dark energy, for all its mystery, requires just one number, Einstein's cosmological constant, to explain cosmic acceleration across billions of years. WIMPs and its cousins, by contrast, need layers of adjustments to match observations, like a tailor endlessly altering a suit that never quite fits. That said, the door isn't closed. Some physicists speculate that both ideas might be pieces of a larger puzzle. Perhaps gravity does behave oddly on galactic scales, and dark energy exists. Others explore quantum gravity theories where space-time's microscopic structure creates emergent effects that look like cosmic acceleration. The debate isn't just academic. It cuts to the heart of whether we truly understand gravity or are mistaking our ignorance for a phantom force. For now, dark energy reigns, not because it's fully understood, but because no alternative explains the universe so completely with so few assumptions. But science thrives on dissent, and every unexplained quirk in the data keeps the embers of rebellion alive. Whether dark energy is real or an illusion, the quest to find out is reshaping physics itself. Right now, as you watch this video, trillions of invisible particles could be streaming through you like ghosts walking through walls, not just occasionally, but every single second of your life. This isn't science fiction, it's the unsettling reality of dark matter's omnipresence. Our solar system, as it orbits the Milky Way, might be sailing through what scientists call a dark matter wind, a relentless cosmic breeze of particles that neither reflect, absorb, nor emit light. Unlike the solar wind, a torrent of charged particles from the sun that creates auroras, this dark counterpart leaves no visible trace. You can't feel it, see it, or shield yourself from it. Yet if detectors like XENO-NNT are right, these particles might occasionally bump into an atom of ordinary matter, leaving behind the faintest whisper of evidence. Deep beneath Italy's Gran Sasso mountain, shielded from cosmic rays by 1.4 kilometers of rock, the XENO-NNT experiment waits like a cosmic microphone tuned to hear those whispers. It's a vat of ultra-pure liquid xenon, chilled to -100 degrees Celsius, where scientists hope a dark matter particle might, against all odds, collide with a xenon nucleus and create a flash of light or a burst of charge. The odds are vanishingly slim. Imagine trying to hear a single raindrop hit the ground during a hurricane. That's how rarely dark matter might interact with normal matter. Yet after years of refining these detectors, researchers have pushed sensitivity to the point where even these ghostly nudges could register. Here's what makes the hunt so tantalizing. If dark matter particles have any mass at all, Earth's movement through the galaxy should create a detectable wind. As our planet orbits the Sun, and the Sun orbits the galactic center, we might plow through denser streams of dark matter at certain times of the year, like a car driving through rain, where the windshield gets hit more intensely when moving forward than backward. Experiments like Xeno-NNT search for these seasonal fluctuations, a potential smoking gun that were not just imagining the signal. The stakes couldn't be higher. A confirmed detection would crack open one of physics' greatest mysteries, revealing dark matter's identity after nearly a century of searching. But the silence so far is just as revealing. Each null result forces theorists back to the drawing board, asking whether dark matter is even rarer, weirder, or more elusive than we imagined. Could it be lighter than predicted, slipping through detectors like sand through a sieve? Or heavier, with collisions so rare we'd need a detector the size of a planet to spot one? Meanwhile, alternative experiments are taking creative approaches. Some hunt for dark matter's gravitational fingerprints in ancient minerals, where passing particles might have left scars billions of years ago. Others use quantum sensors so precise they could detect a dark matter particle's minuscule gravitational pull. It's a global race to catch a ghost one that might require rethinking not just detectors, but our very understanding of how matter interacts, the eerie truth. Even if dark matter is all around us, brushing through your body as you breathe, we might never feel its presence directly. Its dominance over the cosmos is written in the stars' motions and the universe's structure, yet its particles remain stubbornly, maddeningly aloof. Every experiment brings us closer to answering whether we're bathing in an invisible ocean or chasing shadows that demand a whole new physics to explain. Here's the cosmic reality that flips everything you know on its head. The universe you see, everything glittering in telescopes or lighting up the night sky, is just 5% of what's actually out there. Picture a colossal pie sliced into 3 unequal portions. The tiniest sliver, barely a sliver, is the ordinary matter making up stars, planets, and you. The next slice, about a quarter of the pie, is dark matter, an invisible glue holding galaxies together, and the rest, a whopping 68%, is dark energy, the mysterious force accelerating the cosmos apart. That's right, 95% of existence is completely invisible to our eyes and instruments, a shadow universe hiding in plain sight. Think of it like standing in a vast, foggy forest. You can see the trees closest to you, those represent normal matter, but the fog itself, thick and all-encompassing, that's dark matter, unseen but shaping the paths you can take. And the ground beneath you, steadily stretching apart like an invisible conveyor belt, that's dark energy, remaking the landscape with every passing second. Our senses, even our most advanced technology, are blind to nearly everything that actually governs reality. This breakdown isn't just humbling, it's revolutionary. For centuries, science assumed the universe was built from what we could observe. Now we know that's like studying a single grain of sand and calling it the beach. Every time astronomers measure the spin of galaxies or the expansion of space, they're forced to conclude that the material we understand is just cosmic frosting on a cake baked from something entirely unknown. Even the atoms in your body are cosmic rarefications, fleeting specks in a sea of shadow. The implications rattle our understanding of existence itself. If dark matter and dark energy vanished tomorrow, galaxies would fly apart and the universe would rip itself to shreds. We're living in a reality where the visible world is the exception, not the rule, a shimmering illusion propped up by forces we're only beginning to name, let alone comprehend. Every star, every planet, every life form is a flicker in the dark, an afterthought in a universe dominated by the unseen. What if dark matter wasn't born in the Big Bang, but existed before it, a relic from a time before time? This mind-bending idea suggests dark matter could be the universe's oldest inhabitant, a cosmic fossil predating the very explosion we thought birthed everything. Imagine standing at the edge of creation, only to realize the foundation beneath your feet was laid in an era we can't even see. The theory hinges on cosmic inflation, that brief but unimaginable moment when the universe expanded faster than light itself in the first sliver of a second after the Big Bang. But some physicists propose an even wilder twist. What if inflation wasn't the beginning, but just a transition? In this scenario, dark matter particles could have formed during a pre-inflationary phase, a mysterious epoch where the laws of physics as we know them didn't apply. These particles would have survived the Big Bang like stones weathering a flood, becoming the invisible scaffolding for the universe we see today. The implications are staggering. If dark matter predates the Big Bang, it could be a messenger from a reality we can't access, like finding a letter written in a language older than writing itself. Some models suggest these primordial particles emerged from quantum fluctuations in a previous cosmic cycle, or condensed from an exotic energy field that existed before space and time. It's as if the universe inherited dark matter from a parent we never knew, a shadowy heirloom woven into the fabric of existence. This idea also weaves into multiverse theories. If our universe is one bubble in a vast cosmic foam, dark matter might be the residue of collisions with other bubbles, foreign material that seeped into our reality during inflation. Picture two soap bubbles merging. The film between them isn't quite part of either. Dark matter could be that boundary, a remnant of something else clinging to our universe. The evidence, it's subtle but tantalizing. Certain dark matter candidates, like the hypothetical dark photon, could carry signatures of interactions from before the Big Bang. Others, like ultra-heavy WIMPs, might be too massive to have formed in the hot, dense early universe we know, requiring an earlier, cooler environment to emerge. Even the cosmic microwave background's faint anomalies, those tiny temperature fluctuations in the afterglow of creation, could hold clues of pre-bang physics imprinted on dark matter's distribution. But here's the catch: proving any of this is like trying to reconstruct a fire from its ashes. The Big Bang's violence would have erased almost all traces of what came before. Yet if dark matter truly is older than time, it rewrites not just cosmology but philosophy itself. We might be living in a universe built on ruins we can't see, governed by rules written in a language lost to the birth of everything. The hunt for dark matter's origins isn't just about particles, it's about peering beyond the edge of existence, into the unknown that came before. The discovery of dark energy wasn't the result of some grand, targeted search. It was a cosmic curveball, a truth hiding in plain sight until astronomers accidentally tripped over it. In the late 1990s, two rival teams of scientists were studying distant supernova, not to unravel the universe's expansion, but to measure how much it was slowing down. Everyone knew gravity had to be putting the brakes on the Big Bang's outward rush. It was just a question of how much. The researchers expected to find these exploding stars brighter than predicted, their light less stretched by a gradually decelerating cosmos. Instead, the data delivered a shock. The supernovae were dimmer, their light more stretched, as if space itself had expanded faster during its journey to Earth. It was like rolling a ball up a hill, expecting it to slow, only to watch it rocket away faster instead. The teams, led by Saul Perlmutter and Brian Schmidt with Adam Rees, double-checked their instruments, scoured for errors, and reanalyzed the data. The conclusion was inescapable. The universe wasn't just expanding, it was accelerating, propelled by some unseen force stronger than gravity itself. Even more startling, this force made up nearly 70% of the universe's total energy. The finding was so revolutionary, so counter to everything physics had assumed, that the teams hesitated before publishing, fearing they'd missed something fundamental. But the numbers didn't lie. The cosmos had a secret. The key to this accidental breakthrough was the supernova themselves. Type Ia supernova are nature's perfect cosmic yardsticks. They explode with such consistent brightness that astronomers can calculate their true distance by measuring how dim they appear from Earth. By comparing nearby supernova to those billions of light years away, the teams could map how expansion rates changed over time. The distant explosions, whose light had traveled for eons, should have shown the universe's younger, gravity-slowed self. Instead, they revealed a cosmos that had downshifted early on, then mysteriously hit the accelerator. The only explanation, a repulsive force embedded in space itself, dark energy. The irony is thick. These astronomers weren't looking for dark energy, they were chasing a different ghost, the universe's missing mass. At the time, the big debate was whether the cosmos had enough matter to eventually halt its expansion or if it would coast forever. Nobody had seriously considered a third option. That expansion could speed up. Even Einstein, who'd once proposed a similar repulsive force, his cosmological constant, had dismissed it as a blunder. Now his discarded idea was resurrected as the leading explanation for dark energy, a twist so poetic it feels ripped from a sci-fi novel. What makes this discovery so extraordinary is how ordinary the tools were. The teams didn't use some futuristic technology. They relied on decades-old supernova physics and ground-based telescopes. The revelation was there all along, buried in the light of dying stars, waiting for someone to ask the right question. It's a reminder that the universe's biggest secrets often lurk in the gaps between our expectations and reality, in the data that doesn't fit. And sometimes the most groundbreaking truths aren't found by those seeking them, but by those willing to follow the evidence, even when it leads to answers no one saw coming. Deep in the cosmic dawn, before the first conventional stars flickered to life, the universe might have birthed something far stranger: dark stars, colossal infernos fueled not by nuclear fusion, but by the annihilating spark of dark matter itself. Picture a star that doesn't shine in any wavelength we can see, radiating no light, yet glowing fiercely with heat from an invisible power source. These hypothetical giants could have dwarfed the entire solar system, burning dark matter particles as their core fuel in a process so exotic it redefines what a star even is. Here's how it would work. In the early universe, dark matter was far denser than it is today, clumping into vast halos that trapped hydrogen and helium gas. Normally, this gas would collapse under gravity, heat up, and ignite nuclear fusion, the birth of an ordinary star. But if dark matter particles are their own antiparticles, like the theoretical WIMP many experiments hunt for, they'd annihilate on contact, releasing bursts of energy. In regions thick with dark matter, this annihilation could outshine fusion, creating a star stabilized not by outward pressure from nuclear reactions, but by the steady decay of dark matter at its core. The result, a behemoth hundreds or even millions of times more massive than the Sun, its surface temperature lukewarm compared to regular stars, yet its lifespan stretching billions of years longer. The eerie brilliance of this idea lies in how these stars would behave. Without fusion, dark stars wouldn't forge heavy elements like carbon or oxygen, meaning the building blocks of life might have emerged later than we thought. They'd be nearly invisible, detectable only through subtle gravitational lensing or the faint heat they'd emit as infrared radiation. Even more bizarrely, their structure would defy conventional astrophysics, puffy and diffuse, like a red supergiant star stretched to absurd proportions, yet anchored by an engine of pure shadow. Scientists speculate that some of these dark stars might still exist today, lurking in galaxies where dark matter remains densely packed. If they do, telescopes like JWST could spot their infrared glow disguised as unusually massive, cool objects. Others might have met dramatic ends, collapsing into black holes that seeded the supermassive monsters we now find at galactic centers. Either scenario would rewrite stellar evolution, suggesting the first light in the universe wasn't from fusion-powered stars at all, but from something far more mysterious, a celestial relic of a time when dark matter ruled the cosmos. The hunt for dark stars isn't just about adding a new class of objects to astronomy's catalog. It's a test of whether dark matter interacts with itself in ways we've yet imagined. If these giants existed or still do, their discovery wouldn't just solve one cosmic riddle. It would open a window into an entirely unseen chapter of the universe's history, where the rules of physics played out in shadows we're only beginning to trace. The universe isn't just expanding, it's hurtling toward a fate that hinges entirely on dark energy's hidden nature, and the possibilities are more terrifying than any science fiction. Picture 3 cosmic doomsdays, each more dramatic than the last, all dictated by this mysterious force. The first, known as the Big Freeze or heat death, plays out like a slow-motion apocalypse. Galaxies drift apart until the night sky goes black, stars burn out one by one, and space itself becomes a vast, frozen graveyard where even atoms slow to a standstill. This chilling scenario assumes dark energy remains constant, its relentless push stretching space until all energy is diluted into nothingness. But what if dark energy grows stronger over time? Enter the Big Rip, a cosmic shredding so violent it makes the Big Bang look tame. Imagine space itself tearing apart at the seams, first galaxies ripped from their clusters, then stars torn from their galactic homes, planets wrenched apart, and finally, atoms themselves unraveled into subatomic confetti. This nightmare unfolds if dark energy's repulsive force doesn't just persist, but intensifies, overpowering gravity, then electromagnetism, then even the nuclear forces binding matter together. It's the universe's ultimate demolition, where the very fabric of reality is reduced to tatters. Then there's the cosmic boomerang scenario, the Big Crunch. If dark energy weakens or reverses, gravity could regain dominance, yanking everything back into a singularity, a mirror image of the Big Bang. Galaxies would collide in fiery mergers, space would contract like a deflating balloon, and all existence would collapse into a seething, ultra-dense point. Some theories even suggest this could trigger a new Big Bang, birthing another universe in an endless cycle. The uncertainty lies in dark energy's equation of state, a single value determining whether it remains steady, weakens, or escalates. Current observations slightly favor the constant scenario, but even a tiny deviation could tilt the scales toward cataclysm. Upcoming telescopes like Euclid and the Vera Rubin Observatory are racing to measure dark energy's grip across cosmic time, hunting for clues in the stretching of light from ancient galaxies. Here's the haunting truth: our universe's destiny was sealed within its first moments, written in the density of dark energy we still can't explain. Whether it ends in ice, fire, or rebirth, one thing's certain: the force driving the cosmos apart holds the pen that's writing our final chapter. After decades of research, thousands of papers, and countless experiments, here's the humbling truth: we still don't know what dark matter or dark energy actually are. These twin pillars of modern cosmology, making up 95% of the universe, remain as elusive as ever. We've mapped their effects with astonishing precision. How dark matter sculpts galaxies, how dark energy stretches space, but their true nature. That's still locked away in the cosmos's deepest vaults. Consider everything we can't answer. Is dark matter a single type of particle, or an entire shadow universe with its own forces and interactions? Could dark energy be a property of empty space, or a dynamic field that changes over time? Why does it dominate now, after billions of years of gravity's reign? Each question leads to deeper mysteries, like peeling an onion only to find more layers beneath. Even our best theories, from supersymmetry to quantum vacuum energy, feel like vague sketches compared to the intricate reality they're trying to describe. But the hunt is far from over. Next-generation projects are pushing the boundaries of what we can observe. The Vera Rubin Observatory, with its 3.2 gigapixel camera, will scan the entire southern sky every few nights, capturing subtle distortions in starlight caused by dark matter's gravitational grip. Its deep field surveys could reveal if dark energy's strength has changed over cosmic time, a clue to whether it's a constant force or something more volatile. Meanwhile, underground detectors like LZ and future supercolliders aim to shake loose dark matter particles from their hiding places, while space telescopes probe the universe's expansion with unprecedented precision. The most exciting and daunting possibility: dark matter and dark energy might not be separate phenomena at all, but different facets of something even stranger. Some theorists speculate they're linked through higher dimensions or quantum gravity effects we've yet to uncover. Others suggest our very framework for gravity is flawed, needing a radical rewrite to explain these cosmic anomalies. Every null result, every failed detection isn't just a setback, it's a signpost pointing toward uncharted physics. What keeps scientists going is the sheer scale of the mystery. Solving it wouldn't just fill a gap in our textbooks, it would redefine our understanding of reality itself. From the fate of the universe to the fundamental nature of space and time, dark matter and dark energy aren't just puzzles. They're portals to a deeper truth waiting for the right key to unlock them. Until then, we're left staring at the cosmos, knowing the answers are out there, hidden in the dark. From galaxies spinning faster than physics allows to supernova dimming in defiance of gravity's pull, every fact we've explored today points to one inescapable truth. The universe as we know it is built on a foundation we can't see. Dark matter's gravitational embrace holds galaxies together, while dark energy's relentless push stretches space itself apart. Two invisible forces controlling cosmic destiny. Consider the bullet cluster's ghostly collision, where dark matter sailed undisturbed through its own kind, or the eerie uniformity of those Type Ia supernova, their dimming light betraying an accelerating universe. Even the Milky Way's outer stars, whipping around at impossible speeds, testify to dark matter's silent dominance. These aren't just quirks of astronomy, they're clues that 95% of reality operates outside the rules we've written. Think of the cosmic web, that vast neural network of dark matter filaments guiding galaxies into place, or primordial black holes possibly forged before the Big Bang, lurking unseen in the cosmos. Remember Vera Rubin's stubborn pursuit of spinning galaxies, or Einstein's cosmological constant rising from the grave to explain dark energy. Each discovery peels back another layer, revealing how little we truly understand. The quantum vacuum's catastrophic energy mismatch, the unsettling possibility of phantom energy tearing atoms apart. These aren't abstract theories, they're urgent puzzles rewriting physics at its core. Yet for all we've uncovered, the greatest revelations still lie ahead. Will Euclid or the Vera Rubin Observatory catch dark energy's fluctuations across time? Could underground labs finally trap a WIMP, or will we discover dark matter's an entire shadow universe? The beauty of science is that every answer births new questions, and the cosmos always keeps its deepest secrets just out of reach. So stay curious. The next breakthrough might come from a telescope not yet built, a theory not yet imagined, or even from you watching this right now. Which fact reshaped your view of reality? Drop it in the comments, and let's keep unraveling the universe's greatest mysteries together. Because in the end, the most mind-blowing truth might be this: we're just beginning to see the dark.